infinity is weird. In math, infinity is probably one of the concepts that is one of the hardest concepts to think about, and a lot of people have different views about what it means. For example, is infinity a number? And it's like, well, maybe. Feels like a number. Is it on the number line? If it was, it'd have to be something after it, right? And then you get into this whole thing about infinity plus 1. What does infinity even mean if you can add 1 to it? That doesn't make any sense. So maybe it's not a number, maybe it's a size. Maybe it's the size of the number line, right? This goes on forever, and infinity is like the size of this circle that the number line is inside of. I think that's a better way of thinking about infinity, and I hope that in this video I'm going to convince you why. We're going to talk a little bit about the idea of different sizes of infinity in this video. So, different sizes. Different sizes of infinities. Because they do have different sizes. Now, before I start talking about this, I need to get some notation out of the way. Firstly, functions. So, we all know what a function is. A function takes in an input and gives an output. This is a function that maps x to y. Let's say, for example, I said f of x equals x plus 1. And if I had a plane here, I could graph that function quite easily. Functions have what's called an input space and an output space. And I'm not going to get too in depth into what this means, but basically the function that I just gave, the input space is the set of real numbers, and the output space is the set of real numbers. It basically just means the type of thing you can input into the function is called the input space, and the type of thing that you can output from the function is going to be the output space. So, for an example, I could have a function that can only take in, any real number, but it can only output integers. So for example, this would not be valid for that function because it just adds 1 to the number. If I input 3.1, it'll output 4.1, and that isn't in my output space of integers because it's not an integer. But if my function was something like f of x equals x rounded up to the nearest whole number, then this is a fine notion of that function. Because you can see no matter what real number I input, the output will be a whole number. And finally is this idea of bijection. Now a bijective function is going to be, simply put, a function where every input maps to a specific output, and every output is mapped to from a specific input. So let's say, for example, I had a function here that takes things from set A and outputs them to set B. Now A and B can be whatever you want. This can be cats, and this can be triangles or fire trucks. It doesn't matter. They're just sets of things. Now we can imagine if this was set A and this was set B, and we had these things in each. The function is a bijection if for every input there's a unique different output. So this would be a bijection from set A to set B. If anything in here is reached 2 different ways, it's not a bijection. And if anything here is reached 2 ways, it's not a bijection. These are called injectivity and surjectivity, and bijectivity is just a combination of both. So I can give you a quick example of a function that isn't bijective. Let's say f of x equals x squared. Now this once again takes in a real number and outputs a real number. But why isn't it bijective? Well, it's not bijective because I can give you a number that has two inputs that lead to that number. So it would be something like adding a second line here, where an output has two different inputs. That would violate the bijective property. Because for an example, 4 is going to be equal to both f of 2 and f of negative 2. Because 2 and negative 2 both yield 4 when squared. Now, one fact about bijective functions, which is something that we're just going to take for granted in this video, because the proof is going to be a bit more complicated, but if a function from a to b is bijective, then the cardinality of a is going to equal the cardinality of b. Basically, the cardinality in maths is just fancy for saying the size. So if a function a to b is a bijection, a and b had the same number of elements. So you can see in this diagram here that's true. Each thing has 5 elements. Each dot will be like an element. You can imagine that if I added a 6th dot to either side, no matter what I do with my yellow lines, I'm not going to be able to maintain the bijective property. So we're just going to keep this as a fact. If a function from set A to set B is bijective, both those sets A and B have the same size. Now, this is kind of a boring fact, especially if your sets aren't infinite, right? You know, it sort of makes sense. One bijective function would be like capitalizing a letter, because every lowercase letter has a capital component, and every capital letter has a lowercase component. So there's going to be 26 things in my set of lowercase letters and 26 things in my set of uppercase letters. And the process of capitalizing is a bijective function, right? Because the two sets are the same size, and every one input has a different output, and every output had a different input. Now, where infinity gets weird is when we start talking about bijections on infinite sets. For an example, our most basic infinite set, the set of integers. So, real quick question, and just think about what you have an intuition for what you think the answer to this is going to be. Is there more, or are there more, I should say? Are there more integers or even integers? And while you think about that, I'm just going to give some more notation. Let's just let E be the set of even integers. So essentially E is going to be 2x, all the things that can be 2x where x is an integer. It doesn't really matter. Basically, my integers are going to be you know, -1, 0, 1, 2, 3, etc. It goes on for infinity in both directions. My set of evens is just going to be things like 0, or we'll go -2, 0, 2, 4, 6. And the question is, which set's bigger? Well, the intuition is going to be that there are more integers, right? Because it includes odd numbers, and this set doesn't include odd numbers. So surely there has to be more integers than even numbers. But when you consider this definition that says that if I can create a function from A to B, then A and B are the same size, now it becomes a bit more complicated, because I can actually give you a function that inputs any number and outputs an even number, and that function is f of x equals 2x. If this function is the bijection, then these two sets have to be the same size. And it is a bijection, and I hope you can sort of get an intuition for why. Every input has a unique output. So 2 is the only thing that will give me 4, 3 is the only thing that will give me 6, and every output has a unique input. 10, the only thing that gives me 10 is 5, and the only thing that gives me 12 is 6, etc. So this function is a bijection, therefore we can say that the set of integers has the same cardinality as a set of even numbers. If you're familiar with Hilbert's hotel, the idea of this like infinitely full hotel, and you know it's got infinite rooms and everyone's in a room, and then an infinite bus pulls up, then you need to accommodate infinite people. What you can do is you can tell everyone to double their room number, and then all the odd rooms are now free, and all the even rooms are now taken. You might have heard of this thought experiment. That's not really what this video is about, but it's the same basic idea, is that I can actually squeeze a whole extra infinity inside of this infinity because these are the same size. Okay, now let's think of another question about set sizes that uses these ideas. Oh, I'm going to leave in the thing in the red circle. I'm going to leave that, and we'll leave infinity as weird. That's the whole point of the video. My next question to you is, what is there more of? Integers or pairs of integers? So again, the intuition is going to be pairs of integers. There's more pairs of integers because the integers are just going to be, you know, -3, -2, -1, 0, 1, 2, whatever. The pairs of integers are going to include, you know, -3, +4, and -2, +8. There's way more combos, it feels like, right? Well, let's see. If I can form a bijection from one set to the other, then they are by definition the same size. So how am I going to visualize my pairs of integers? Well, we can draw what's called a lattice grid, which is just going to be my Cartesian plane that goes on forever. And I'm going to put a bunch of red dots, and every dot represents a different pair of integers. So the one in the very middle is 0, 0. This one here that I'm about to place, this one here, is going to be 1, -2, right? It doesn't matter, but hopefully you can see that all these dots represent a pair of integers. And it goes on forever in every direction, so this is going to keep going forever. If I can create a function that takes in an integer and outputs a pair of integers uniquely in a bijective way, then I've shown that the sets are the same size. And well, I can sort of do this visually. Imagine if I have a piece of string, a yellow piece of string, let's make it a blue piece of string, and it starts here, and I slowly unravel it, right? And I'm covering up every pair of integers, like a spiral. And I'm going to go on forever. Well, how many points are on the string? Well, one for every natural number, because it goes on for infinity discretely. And so what I've done now is that I've, using just the natural numbers, I've covered up every pair of natural numbers. So I've kind of gone from a one-dimensional shape to a two-dimensional shape and filled up all the space. Therefore, the cardinality of the integers is equal to the cardinality of the pairs of integers. Interestingly, a rational, and we talked about this in the last video, a rational number is kind of like just a pair of integers because it's just a over b. Right? A rational number can be expressed as a ratio of two integers. So to get any rational number, all you need is two integers. So I can make the exact same argument to tell me that the cardinality of the integers is the same as the cardinality of the rationals. That is that for every integer, there is a rational. Alright, now it's time for the big one, and this is the point of the video. And remember, we're talking about different sizes of infinity. I'm going to try and argue that there are infinities bigger than the size of the integers. So, what's bigger? A set of integers or the set of reals? Now remember, a real number includes the irrationals as well. So it still includes all the ratios of integers, it still includes a half, a third, all that stuff, but it also now includes things like pi and root 2 and e. These are all things that we spoke about in the last video. Now what's bigger? Well, again, if I can form a bijection between the two, then I can prove that they are the same size. And I'm going to try and show you why I can't. So again, we're going to do what's known as a proof by contradiction, which is where you assume something's possible that you don't think will be possible and look for a contradiction. Look for a reason why the world breaks, and when it breaks, you know that, well, you must have broken a rule by even assuming it was possible. So, proof of contradiction, let's assume for the sake of argument, assume that there exists such a bijection from Z to R. Now this is not very formal, but instead of Z, I'm actually going to use N, which just means the natural numbers. Basically just means all the integers, but I'm getting rid of the odd ones. It shouldn't matter, and hopefully you can see how these are going to be either the same size or this is smaller. They actually are the same size, and I can give you a bijection to show that, but it shouldn't matter because this is going to have, everything in here is going to be an integer. So I'm just going to show bijection from the natural numbers to R. Assume that there exists such a bijection. Well, if there does, I should be able to draw it. So we're going to try and draw it now. These are going to be my natural numbers, and these are going to be my real numbers. Well, in my natural number column, I can just start laying them out. 1, 2, 3. I think we'll count 0 as a natural number. It shouldn't matter for the proof, but yeah. 0, 1, 2, 3, 4, 5, and it's going to go on forever. Now in my real number column, we could just start filling them out. So we could just start saying something like, well, 0.1432, 0.2896, and go on forever. And the idea is that if this table can, and these go on forever in this direction as well. The idea is that if this table can be filled out properly, then the sets have to be the same size. And I'm going to try and argue that they can't be filled out properly. So let's generalize a little bit, and let's give these values arbitrary digits. So instead of 0.6942 whatever, let's give them names. So let's say this is going to be 0.A1, B1, C1, D1, etc. And then these ones can be A2, B2, C2, D2, etc. And you can see where I'm going with this. It's going to be A3, B3, C3, D3, etc. And I'll draw one more and then we'll stop. So, but you see the idea here. You might be thinking, well, you know, there's only 64 letters. So, sorry, 64. There's only 26 letters. Sorry, I keep fucking up. Yeah, cool. There's only 26 letters. So, what's gonna happen when you reach the end? Well, then after that, we'll just use AA and then AB and then AC. The idea is that it will fill up forever and infinity in this direction as well as this direction. So we're doing a proof by contradiction. So let's assume that this table is full, as in there are just as many integers as there are natural numbers. If they're full, then can I think of a new number to add to the set? Well, no, right? Because it's full. I've used all the natural numbers. There's no natural number you can give me that I haven't used. What about this set? Well, let's make the first number differ from A1. So it's different from this number. Let's make it A1 plus 1. This is just a digit. So A1 plus 1. And if A is 9, let's just wrap it around to 0. So we can actually give a proper function here that we're going to say that it's going to be f of x equals, we'll say x plus 1 mod 10. without getting too specific into what this means, basically we're just going to wrap it around like the hands on a clock. So if I'm going to add 1 to the number, unless the number is 9, in which case I'm going to make it 0. So it's just going to change the digit in some way. Now my next digit, let's make it differ from this number in the second column. B2 plus 1. And then my next number is going to differ from the third digit, the third number in the third column, C3 plus 1. And what I'm going to do here is I can keep doing this forever with all these numbers, and I have created a brand new real number that I haven't used before, and I know that it's brand new because it differs from the first number in the first column. It differs from the second number in the second column. It differs from the third number in the third column. It differs from the fourth number in the fourth column. In general, it differs from the nth number in the nth column. So this bijection can't exist, because if it existed, this number would have to have already been used, but it hasn't already been used. Therefore, these aren't the same size. So my takeaway here, and I probably should scroll down a bit because I don't know if the watermark is getting in the way. What we've shown here is that there are a larger number of real numbers than there are integers. Which is weird because the amount of integers is already infinite. So now we have a bigger infinity that we've created. Let me say something else about this. I'm not going to show the proof here, but there's a certain thing you can do to a set called create a power set. The power set of a set means the set of all subsets of that set. So the power set of X, so let's say that X is a set and it's got a 1 and a 2 in it. The power set of X is going to be a set with all the subsets. So we have an empty set, that symbol means empty set. We have the set with just the 1 in it. We have a set with just the 2 in it. And we have a set 1, 2, which is X itself. Cantor, who is the mathematician that did that other argument I just showed, has shown that for any set X, the size of its power set is going to be strictly bigger than the size of the set itself. Now what that means is that, well, we've shown that there are more real numbers than there are integers. There's more numbers in the power set of the real numbers. And there's more numbers in the power set of real numbers. What this means is that I can do this forever, and I have created an infinite hierarchy of infinities. These infinities are going to get bigger and bigger and bigger, but they're all infinity. These are all infinity, even this one. This is the smallest infinity. It's what we call a countable infinity. So, yeah, infinity is weird, and it's still a bit debatable if Cantor can even make these arguments. But this is why I think infinity is best thought of as a size and not as a number. Because if infinity was a number, you couldn't do this kind of thing. But if infinity was a size, or more specifically a cardinality of a set, then all this math becomes possible. And all it required was this idea here, that if two functions are bijective, then they're equal. So if in real life, if you want to figure out if two things have the same size, if you can line them all up and put them to pairs where one relates to another one, it is the same size. Interestingly, when we count things in real life, what we're kind of doing is forming a bijection between those things and the numbers. So if I put 30 marbles on the floor and I have to count them all, I point at the first marble and I say 1, and then I point at the next one and I say 2, and I keep going until I hit 30. What I've done is I've created a bijective function, or a bijection, between the first 30 natural numbers and the 30 marbles. And I've shown that those two, because I made a bijection, that means those two sets are the same size, meaning they both contain 30 things. And that's how I know that there are 30 marbles on the floor. The cavemen did this, so we've already sort of figured it out. But yeah, anyway, that's all I have to say about infinity and bijections. Infinity's weird. Thanks for watching.